Hi friends, so welcome to my channel. Today we are going to start lecture 51 on the helicopter dynamics course. And today I am going to talk about the velocities at the cross section which the blade sees in forward flight or the blade section sees in forward flight. I am Dr. Ranjan Ganguly. Now if we see the rotor disc, it's typically in this manner and has an inclination in forward flight. So the velocity comes from the forward direction. You have the rotor disc here, and therefore the velocity can be resolved into two components. One is a sine component that's in the vertical direction, and one is a cos component that's in the plane of the rotor disc. Now we have seen that this sine component gets summed with the induced velocity and becomes a part of the up expression for the velocity, that is the perpendicular component. So today we are going to focus on this component which is tangential, that's in terms of the cosine. So this rotor disc is typically tilted, and this tilt alpha is the rotor disc AOA, and it is positive for forward tilt of the rotor like I showed in the previous slide. Now also recall that the non-dimensional forward speed mu is V into cos of alpha divided by rotation speed into blade radius. So this is the non-dimensional forward speed. So now let us take a look at the rotor disc from the top view. So remember, the velocity comes in front. So now we know that this velocity is essentially mu. So we can put mu here. And if we look at any point on the blade section here, we will see that we can resolve mu into a component which is mu sine psi, and this is the component which comes tangentially to the blade section at a given radius r. Okay, so if we zoom into this particular section, we can clearly show that the mu is coming in front, and because this blade is at some location psi, from size 0 degree here, the component in this direction is mu into sine psi. And also you can imagine that there is going to be one more component here which is mu into cosine psi, that is the radial component. So we can split this mu into two parts at a given blade section, that is going to be mu sine psi, which is the tangential velocity, and mu cosine psi, which is the radial velocity at a rotor blade section. And recall that this is at a section R on the blade at which you are currently located. Now you need to add the rotational speed component to ut. So the tangential component becomes rotation speed plus mu sine psi, and the radial component becomes mu cos psi. Okay, because mu is defined as follows. Now I can go back to mu and write it out in this manner. So this is ut and ur, and then I can non-dimensionalize both ut and ur with respect to rotation speed into radius, and this is going to give me this particular non-dimensional quantity. So ut is going to be small r by capital R plus mu sine psi, and ur is going to be mu cosine psi. Now let us look at something known as the reverse flow region. So one of the things you will realize if you look at the equation for ut for a long time is that the second part, which is the term involving mu sine psi, becomes negative in some parts of the rotor disc. And this is because psi is varying all the way from 0 to 360 degrees. So especially in the region which is between pi and 2 pi, that is between 180 and 360 degree, sine psi will become negative. And therefore you are going to encounter certain flow situations where ut is actually negative and where the component of the velocity which is due to forward speed is greater than the rotational component. Now remember, when you are on the side of the rotor where this is happening, these two components are getting subtracted because the sign is negative, and therefore you are encountering a reverse flow situation with ut less than 0. So we want to find this location of reverse flow, so we can find it from the equation. So ut is less than 0 when this condition is satisfied, and therefore this condition, if we want to zoom in it in greater detail, we will put psi is 270, so sine psi is minus 1, and we encounter this simpler formula which gives us that mu would be small r by capital R, and that would be the length in which this reverse flow will happen at sine psi is minus 1. So if we look at it on the rotor disk, essentially you have a circular region here, and this region is the location where reverse flow happens. That means in this region the airfoil section will see the flow coming from behind rather than from front. So this is not something which is good because the airfoil sections are typically not designed for such a flow, and therefore the performance of the airfoil section in this regime is going to be subpar, not as good as you could get in a regular flow situation. Now, the advance ratio of a typical helicopter ranges from zero point 0.2 to zero point 0.3. Therefore, from our previous picture, we can assume that 20 to 30% of the retreating side is in reverse flow in forward flight. And what this is going to do is it's going to greatly impact some of the aerodynamic forces which are going to be generated by this particular part of the rotor, and therefore reverse flow is going to increase the asymmetry which you get in forward flight. So this is something which you have to deal with, and the faster the aircraft flies, the more the reverse flow region is going to become, because it's directly proportional to the value of mu. So now let's take a step back and go back to our equation for ut and ur. So you are going to immediately realize that the presence of forward flight, which essentially comes in through this mu term, leads to the presence of sine psi and cosine psi in these equations for velocity. Now remember, when mu was 0, these were just functions of small r, which is the radial station on the blade. So therefore the blade loads and motion are going to become also functions of sinusoidal functions, or sine psi and cosine psi. And in fact we can see right here that because lift, drag and all are dependent on u square, the square terms will come in terms of sine and cosine, and they are going to therefore give you sine 2 psi, cos 2 psi content. So therefore you are going to get harmonic content in this particular forcing function. So the net result of this is that the blade loads and motion all essentially become functions of psi here. And also recall that up is a function of lambda, and that also is typically varying with respect to r and psi round the rotor disk. So essentially one of the things which happens in forward flight is that the blade response is periodic. Therefore I can say that beta, zeta and theta, which are the flap, lag and pitch motion, are all now functions of psi. And also the corresponding blade forces, blade moments are all also going to become functions of both r and psi, whereas when there was no forward speed, our condition, they were function of radial station only. So that's a big complication which has come because of the presence of forward flight. Now, what happens in steady state? What do we mean by the steady state condition? Well, in steady state, the behavior of the rotor as it revolves is the same at a given psi location as it goes through different revolutions. Okay, so it does not change as the revolutions are going through. Now, before you settle into steady state, there is something known as transient, and transients essentially vary with the different revolutions. But what happens is that transients will typically die out due to damping. We already saw that some of the modes, such as the flap modes, are well damped because of presence of the beta dot or beta star terms. But also there is structural damping in the system. There may be dampers put into the system, such as for lag damping and so on. So the effect of all this damping, both coming from fluid mechanics and structures, is to decimate the transients. So therefore, the steady state is the one which survives in typical cruise flight conditions, and most of the flight condition of the vehicle is going to be spent in the steady state region. And that is why we spent a lot of time in calculating the blade loads and motion in steady state, where they are essentially periodic with period 2 pi, because we saw that these forcing functions typically come from sine psi and cosine psi, which then may be squared and so on, but they are all going to be essentially periodic functions. So mathematically, if we look at steady state forward flight, we see that the blade response, so we are going to slowly start calling the blade response as Q as a more general nomenclature. So beta, zeta, theta are all functions of psi, therefore Q is going to be a function of psi. And F are the loads which act at any given section. So we can say that these are in the X, Y, and Z direction. There are three forces and three moments. So these are going to be functions of psi, and also they are going to be periodic. So I can write Q0 equals Q2 pi, F0 equals F2 pi in general. And also Q psi is Q psi plus 2 pi, F psi is F psi plus 2 pi. Therefore, we focus on only one revolution. We don't have to necessarily solve this differential equation across time as is generally required for systems where you are also looking at the transient. Of course, if you are calculating for both the transient and the steady state, you will have to solve the rotor dynamics equations in general across time with some initial conditions. But if you are only concentrating on getting the steady state value, you may be able to solve it only for the steady state condition after the transients has died out. And there are some methods to get the steady state response which are present by basically presuming the response to be periodic and also trying to enforce periodicity condition through some kind of mathematical means. So we'll conclude this lecture here. We will continue in our next lecture on this development of the loads and so on for the forward flight situation. See you then.